Hi, we'll talk about the basic idea behind insertion sort in this video. So insertion sort is in some ways it's kind of similar to a bubble sort. Most importantly, it's still quadratic, so it's not terribly fast, but it is nice to study it for quite a few reasons as I list them out here. So first, it's very simple. As you can see in the code, it's just a few lines of code. And while we say it's generally not very fast, it's quite fast for a small list. And despite the fact that it's quadratic, same as bubble sort, it is faster than bubble sort. And also, if the input list is almost sorted, then it's fast in that it's almost linear. And then it can kind of very naturally sorts the list in place, just the way it works. And then it's one of those sorts that's quite interesting in that it can sort the new elements as they kind of come in, over say some sort of input stream or over the network. Because, well, I mean, as the name suggests, it's inserting them right into an already sorted list. And then finally, it's important to understand it because it forms the basis for what's called a shell sort, which is a lot faster. And as I mentioned earlier, sorting really has its kind of roots in our daily lives, because in our daily lives we do different kind of sorting all the time. So for example, if you play bridge or any sort of card game and you want to kind of sort through the cards in your hand, you're likely already performing something very similar to an insertion sort. And so the basic idea is at any step, any iteration in this algorithm, the list of elements, they are divided into two parts, the sorted part and the unsorted part. And then at each step, we just take an element from the unsorted part, insert it into its right place in the sorted part, and then we just keep repeating the process until everything is sorted. To demonstrate the idea of insertion sort, so let's look at a concrete example. Here is a list of 5 elements: 6, 2, 3, 1, and 8. So as I said, we divide this list into two parts. The left part is sorted, and then the right part is unsorted. Now we can start with the sorted part having a single element, because a list with a single element is always sorted. Okay, so and the next thing we do is we take the first element from the unsorted a section of the list 2, and we try to insert it into the right place in the sorted section. And we know 2 should come before 6, and that's what happens. And then once that is done, the sorted part is grows by 1 element, and the unsorted part shrinks by 1 element. So we repeat the process. We take the first element from the unsorted part, and then again we insert it into the sorted part. 3 goes between 2 and 6, and that's what we end up with. And so we keep going. The next thing, we take 1 from the unsorted part, try to insert it. It goes to the beginning of the sorted section, and then finally we try to insert 8 in it. 8 doesn't need to move, it's already in the right place. So, and there we're done. So having seen a demonstration of how insertion works, now it's your turn. So try given this list of numbers, try to sort them using insertion sort. And if you want to verify your answer, I actually just take this example from the Wikipedia, so you can go to this link and make sure that the step you went through is the same as what's shown on Wikipedia. So another problem is given a list 1, 2, 3, 4, 5, and try to run through the insertion sort and see how it works. But more importantly, what is the big O of this? So pause the video, give this a try. So assuming you've done that, I mean, it's obvious that this list is already sorted. But the more important thing is, how long does it take for insertion sort to go through the entire list and then realize it's something that's already sorted? Well, the number of steps should be basically on the order of n, right? Because let's say we start with number 2. It takes one comparison uh, with 2 and 1 to realize, well, 2 is already in the right place. And then we'll move on to 3, and it takes one comparison to know that 3 is already in the right place, and then so on. Same thing for 4 and 5. So it basically just take out of n steps to see that, oh, the entire list is sorted. And this is the best case scenario for insertion sort. So as we said earlier, in a sorted list or in a nearly sorted list, it's on the order of n. And that is great. That is actually the best that any sorting algorithm can do in that particular scenario, because you do have to at least look through the entire list once to realize something is already sorted. And believe it or not, you'll be seeing example of this later, that not all sorting algorithm can do this. Some of the sorting algorithm will take forever to recognize that the list is already done. But so this is actually one very, very big advantage of insertion sort. Okay, what about this list? Can you sort it with insertion sort? Well, okay, so if you do that, you will see that this is actually the worst case scenario for insertion sort, this list that is sorted in exactly the reverse order. So because it takes just one comparison to put 4 in the right place. It would take 2 comparison to put 3, because 3 now has to go all the way to the beginning. And then again, for 2, it will have to travel the maximum distance to the beginning. And then 1 also has to do the same. So this is, again, absolutely the worst case for insertion sort. And in general, as you can kind of see, it would take 1 plus 2 plus 3, etc., all the way to n, or probably n minus 1, off by 1 here, steps for the insertion sort to sort in this worst case. And if you remember the formula for the sum of the series, that's n minus 1 times n over 2, and that is therefore big O of n squared. So this is what gives insertion sort its quadratic time. And then finally, on the average case, remember in the worst case is every element has to travel all the way the entire length of the list to the beginning. But then on average, it's probably, rather than travel the entire length of the list, it probably travel, half of the length. So it would be half times this number here, and but constants really don't matter in the world of big O. So the average case is also big O of n squared for insertion sort.